Hello, and welcome. As you settle in, take a moment to notice the quiet. Maybe you hear the gentle shift of air outside your window, or perhaps the distant, steady rhythm of the world going on without you. Tonight, we begin a new session of Sleepy Science, where we journey into the one massive, chaotic system that runs on total, perfect predictability: the weather. Our goal is simple: to help you get sleepy by slowing down the complex science of the sky. Every gust of wind, every quiet cloud drift, it's not random. It is an act of balance. It is the sound of the entire planet breathing. Let your thoughts drift like clouds. Our journey begins with the largest, quietest truth of all: the sun's unequal light. The entire giant system we call weather runs on one simple idea: the planet cannot stand to be uneven. Think of our world like a marble that the sun only warms fiercely in the middle, the equator. The light hits here, making it intensely hot. But up at the poles, the same light spreads out and barely touches the ground, keeping those regions deep in the cold. This difference is an energy debt. The middle of the planet has too much heat, and the top and bottom have too little. And the world's most massive work is simply trying to settle that debt, to share the heat. All of the wind, all of the storms, all the movement in the sky is the atmosphere and the ocean working patiently and endlessly to balance the books. That tireless search for balance is the core of our weather. This great heat-moving machine works inside a very thin, precious layer of air we call the atmosphere. It's stacked in layers, but for us, only the first matters: the troposphere. The troposphere is where everything happens. It's a very thin shell, only going up about 12 kilometers, but it holds almost all the air and water on the planet. This is where the air is warmest near the ground, like a room with the heat on the floor, and gets steadily colder as you rise. This gentle cooling is the perfect, essential condition that allows invisible water vapor to slowly turn into clouds. This great heat-moving machine works inside a very thin, precious layer of air we call the atmosphere. It's stacked in layers, but for us, only the first matters: the troposphere. The troposphere is where everything happens. It's a very thin shell, only going up about 12 kilometers, but it holds almost all the air and water on the planet. This is where the air is warmest near the ground, like a room with the heat on the floor, and gets steadily colder as you rise. This gentle cooling is the perfect, essential condition that allows invisible water vapor to slowly turn into clouds. Above this layer, the stratosphere and its ozone shield hold the chaos in, acting like a firm, quiet lid. Our weather stays right here, in this thin, warm-bottomed layer, trapped and contained. We live with the quiet weight of the air on our shoulders, about 15 pounds on every square inch of our body. This is the atmospheric pressure. Changes in this pressure are the only thing that creates the wind. When air gets warm and light, it softly rises, creating a low-pressure system. These are the areas where clouds and change gather. When air gets cold and dense, it gently sinks, creating a high-pressure system, bringing clear, still, and calm skies. Wind is simply the soft, continuous flow of heavy air rushing to fill the void left by the light air. It is the atmosphere trying to level itself out, a constant whisper of correction. The Earth's high-speed, quiet rotation is the final ingredient. Our spinning planet creates an illusion that bends every large movement of air into a curve, the Coriolis effect. The rule is simple. Air and water swerve to the right in the north and swerve to the left in the south. This invisible, constant push is what takes the straight flow of the wind and turns it into the massive, gentle spirals we see in the clouds and ocean currents. It's the planet's slow, powerful twist that keeps the whole system connected and in motion. Water vapor, the invisible gas form of water, is the atmosphere's most powerful secret weapon. It is the fuel, the storage battery, and the greatest source of energy for every storm on Earth. When water evaporates from the ocean, it stores heat. This hidden energy is called latent heat. Think of humid air, like air filled with tiny rechargeable batteries. When that humid air rises and cools, the water vapor must change back into liquid, a process called condensation, to form a cloud droplet. And here's the magic. When it condenses, it releases that stored heat energy back into the surrounding air. This released heat makes the air lighter and warmer, giving it a powerful boost to rise even higher. This feedback loop, rising, condensing, releasing heat, and rising again, is the primary engine that makes a tiny cloud grow into a colossal, multi-mile-high thunderstorm. Above this layer, the stratosphere and its ozone shield hold the chaos in, acting like a firm, quiet lid. Our weather stays right here, in this thin, warm-bottomed layer, trapped and contained. A typical puffy cumulus cloud can hold hundreds of thousands of tons of water, heavier than 1,000,000 elephants standing side by side. And yet, the cloud floats, suspended because the water is spread out into countless microscopic drops. The sight of something so immense, so heavy, yet appearing delicate and ethereal, is one of the great paradoxes of weather. Before that cloud can even form, the water vapor needs something to hold on to: condensation nuclei. These are microscopic dust particles, specks of pollution, or tiny crystals of sea salt. Every single cloud droplet formed around one of these tiny specks. Without the planet's dust, we'd have no clouds. And the raindrops that fall are not teardrop-shaped at all. As they grow, air resistance flattens their bottoms, giving them a shape more like a hamburger bun than a teardrop. Finally, the unique, earthy, comforting fragrance that rises after a rainstorm is called petrichor. It's a mix of ancient oils released by microbes in the soil, and often ozone created by lightning. As warm, invisible air rises, it expands. When air expands, it cools, a process called adiabatic cooling. When it cools to the dew point, it forms clouds at the lifting condensation level, LCL. Every cloud name tells a story: cumulus, puffy; stratus, layered; cirrus, wispy; and nimbus, rain-bearing. The towering giant that ignores all the rules is the cumulonimbus cloud, the thunderstorm. It punches through the upper atmosphere, forming a flat anvil shape when it hits the stable layer of the stratosphere. As warm, invisible air rises, it expands. When air expands, it cools, a process called adiabatic cooling. When it cools to the dew point, it forms clouds at the lifting condensation level, LCL. Every cloud name tells a story: cumulus, puffy; stratus, layered; cirrus, wispy; and nimbus, rain-bearing. The towering giant that ignores all the rules is the cumulonimbus cloud, the thunderstorm. It punches through the upper atmosphere, forming a flat anvil shape when it hits the stable layer of the stratosphere. The global conveyor belt. The atmosphere organizes itself into three massive, looping belts in each hemisphere. The Hadley cell creates rain near the equator and sinking dry air around 30 degrees latitude, which is why all the world's great deserts are found there. The polar cell circulates cold, heavy air near the poles. The feral cell, the unstable middle zone where tropical and polar air collide, creating the polar front, the battleground where most storms are born. Air masses are huge chunks of air that don't mix easily. When they collide, they form weather fronts. Cold front. Heavy, dense cold air drives under warm air like a bulldozer, forcing a rapid lift that creates thunderstorms. Warm front. Lighter, warm air glides slowly up and over the cold air, creating gradual lift, leading to long periods of light, drizzly rain. High above the polar front flows the jet stream, an invisible ribbon of air moving up to 400 kilometers per hour. It meanders in massive waves. Troughs, dips south, pull frigid air, causing cold snaps. Rides, bulges north, funnel warm air, causing heat waves. It is the ultimate global controller, determining the path, speed, and severity of all mid-latitude weather. The most dangerous storm is the supercell, which is an organized, rotating storm. It requires wind shear, a drastic change in wind speed or direction between low and high altitudes. This creates a horizontal tube of spinning air that the storm's powerful updraft tips upright, causing the entire storm cloud to rotate, a mesocyclone. Before a supercell unleashes its full power, the sky can sometimes turn an eerie, unsettling green. This happens when sunlight filters through the immense amount of ice and water in the storm, amplifying the green wavelengths, signaling that a storm is strong enough to produce large hail and a possible tornado. When the rotation inside the supercell stretches downward to the ground, it spins faster, the ice skater effect, and becomes a tornado. Its winds can reach up to 480 kilometers per hour. One of the strangest pieces of evidence of its power is that lightweight straw, caught in the vortex, can be accelerated to such extraordinary speeds that it can be driven straight through solid wood fence posts. A hurricane is a colossal, spiraling engine fueled by warm ocean water, at least 26.5 degrees Celsius. The storm is powered by the massive release of latent heat from condensing water vapor. The energy released by a single hurricane in one day is greater than the energy used by all of humanity's power plants combined in the same period. At its center is the eye, a circular region where the air clears and calms, surrounded by the eye wall, the deadliest ring of wind and rain. The polar vortex is a mass of icy air swirling high above the Arctic. When the winds that contain it weaken and wobble, this extreme cold can spill southward, causing sudden, record-breaking cold snaps and temperate zones. Even in the cold, avalanches can accelerate to speeds faster than cars on a highway. The massive, hidden bulk of icebergs, only 10% of which is visible, slowly melts, altering ocean currents. The Atacama Desert in Chile is so dry that some parts go decades without rain. Conversely, Mawsynram in India receives over 12 meters of rainfall annually. The temperature extremes on Earth span from negative 89.2 degrees Celsius, negative 128.6 degrees Fahrenheit in Antarctica, to 56.7 degrees Celsius, 134 degrees Fahrenheit in Death Valley. In deserts, dew is a quiet savior. As the ground cools, moisture condenses onto sand and rocks, sustaining life where rain is impossible. The principles of heat, pressure, and spin are universal. On Jupiter, the Great Red Spot is a colossal cyclone wider than Earth, spinning for centuries. Saturn's hexagon is a giant, stable, six-sided storm larger than Earth. Neptune's supersonic winds are the fastest winds recorded on any planet, reaching 2,100 kilometers per hour. And on exoplanets, extreme heat causes the skies to fill with clouds of vaporized silicates, resulting in horizontal rain made of glass or even molten iron. The atmosphere is a giant lens, creating illusions. A rainbow is a full circle of light, though we usually only see the arc. A double rainbow is created by light reflecting twice inside the drops. Mirages occur when light bends through air layers of different temperatures, creating illusions of water, inferior mirages, or floating ships, superior mirages. Fulgurites are hollow, glassy structures etched into the sand by the fierce heat of a lightning strike, a lightning fossil. Animals are the planet's most sensitive barometers, detecting tiny drops in atmospheric pressure before storms arrive. Birds will flee, cows may lie down, and the entire 4,800-kilometer migration of the monarch butterfly is a colossal act of atmospheric navigation. Even the ache in human joints before rain is a physical reaction to the pressure drop. Modern prediction relies on satellites. Geostationary and polar orbiting eyes provide global, minute-by-minute views of cloud movement and moisture. Doppler radar tracks the speed and direction of raindrops, allowing meteorologists to see inside a storm's rotation for tornado warnings. Supercomputers run complex calculations to simulate the weather's future, acting as a giant brain to predict paths days ahead. The atmosphere is a chaotic system, exquisitely sensitive to the smallest change, the butterfly effect, making long-term prediction impossible. Humanity is introducing a massive shift by thickening the atmospheric blanket with gases like carbon dioxide. This leads to amplified extremes. A warmer atmosphere holds 7% more water per 1 degree Celsius of warming, fueling stronger hurricanes and heavier floods. The precipitation whiplash, dangerous swings between long, intense droughts and sudden, overwhelming deluges. Sea ice loss. The melting of Arctic ice exposes dark ocean water, which absorbs more heat, accelerating warming and disrupting the global circulation patterns. The constant push and pull of air isn't just a north-south affair. It involves complex vertical and horizontal waves. High above the equator, for example, is a massive wind cycle known as the quasi-biennial oscillation, QBO. This huge wind current high in the stratosphere reverses direction every 28 months, switching from flowing eastward to flowing westward. This distant, upper atmospheric current has subtle, traceable influences on the formation of storms, the path of the jet stream, and even the severity of northern hemisphere winters. It proves that the entire atmosphere, even in its highest, thinnest layers, is a complex, interacting machine. The atmosphere also moves heat through subtle thermal layers in the ocean. The deep ocean currents we discussed are not only driven by cold and salt, thermohaline, but also by wind. The wind shear across the water's surface creates a complex spiral pattern of water movement called the Ekman spiral. Surface water is pushed by the wind, but the Coriolis effect nudges it to the right, in the north, and each layer of water below is nudged even further right, creating a vast, slow spiral motion that transports both nutrients and heat across massive distances. This means that wind, in its constant friction against the sea, is shaping the ocean's very pathways. The atmosphere also moves heat through subtle thermal layers in the ocean. The deep ocean currents we discussed are not only driven by cold and salt, thermohaline, but also by wind. The wind shear across the water's surface creates a complex spiral pattern of water movement called the Ekman spiral. Surface water is pushed by the wind, but the Coriolis effect nudges it to the right, in the north, and each layer of water below is nudged even further right, creating a vast, slow spiral motion that transports both nutrients and heat across massive distances. This means that wind, in its constant friction against the sea, is shaping the ocean's very pathways. The atmosphere also moves heat through subtle thermal layers in the ocean. The deep ocean currents we discussed are not only driven by cold and salt, thermohaline, but also by wind. The wind shear across the water's surface creates a complex spiral pattern of water movement called the Ekman spiral. Surface water is pushed by the wind, but the Coriolis effect nudges it to the right, in the north, and each layer of water below is nudged even further right, creating a vast, slow spiral motion that transports both nutrients and heat across massive distances. This means that wind, in its constant friction against the sea, is shaping the ocean's very pathways. The atmosphere is constantly being changed, not only by its own forces, but by what the surface gives it. We discussed the massive Sahara dust plumes, but the scale of smoke and ash injection into the atmosphere is equally important. Volcanic eruptions are the most dramatic example. When a volcano erupts explosively, it blasts ash and gases high into the stratosphere. Tiny particles of sulfur dioxide can linger for months or even years, reflecting sunlight and cooling the entire planet's surface. The eruption of Mount Tambora in 1815 was so powerful it caused the year without a summer, bringing frost and famine across the northern hemisphere. The fire of the earth itself has a voice, whispering through the clouds and shifting the global energy balance. Forest fires also create their own localized weather systems. Intense heat drives powerful updrafts, lifting ash and smoke into the sky. Inside these clouds, particles collide, generating static electricity, much like a normal thunderstorm. This forms pyrocumulus clouds, storm clouds born from fire, that can unleash their own lightning bolts back down onto the burning forest, creating a cycle of flame feeding on itself. This shows that the landscape is not just a victim of weather, but a creator of weather. The city, the volcano, and the burning forest all add their own unique recipe to the air. Let's return to the ground and examine how the smallest local conditions create unique weather. Orographic lift, the air being forced up by mountains, is only part of the story. The rain shadow on the leeward side of the mountain can also experience strange, warm, dry winds called foehn or chinook winds. As the air descends down the mountain slope, it compresses and warms rapidly. These winds can raise temperatures by 10 or 15 degrees in just an hour, creating sudden, dramatic thaws that can be both welcome, melting snow, and dangerous, raising fire risk. Even in completely flat areas, the surface creates distinct microclimates. A huge field of corn or a massive forest canopy releases vast amounts of moisture through transpiration, water vapor released by plants. This process creates a cooler, moister air mass directly above the vegetation, compared to a nearby bare field. If that warm, moist air is lifted high enough, it can start its own convective storm. The invisible action of a massive forest essentially fuels its own rain cycle. The subtle differences in how a plowed field, a dense forest, or a city park exchange moisture and heat with the air are constantly contributing to the regional weather map. Every small detail on the ground matters to the sky. The vast majority of modern weather research is dedicated to understanding how the new human-made variables will affect the large natural cycles. One area of critical study is the ocean's absorption of carbon dioxide. The ocean is a massive carbon sink, absorbing huge amounts of CO2 from the atmosphere. This is vital because it slows the warming process, but it has a dangerous side effect: ocean acidification. As the ocean absorbs more carbon, its pH level drops, making it more acidic. This impacts marine life, particularly shellfish and coral reefs, which struggle to build their calcium carbonate shells in acidic water. The atmosphere's attempt to find chemical balance with the land is causing a crisis beneath the waves. Another key area is the study of permafrost. In the frozen Arctic and Siberia, vast areas of ground have remained frozen for thousands of years, permafrost. This frozen ground locks away ancient carbon, dead plants, and organic material. As the climate warms, this permafrost thaws, releasing massive amounts of methane, a greenhouse gas far more potent than carbon dioxide. This creates a dangerous feedback loop. Warming thaws the permafrost, which releases methane, which causes more warming, which thaws more permafrost. These silent, underground changes are critical tipping points in the Earth's weather engine. The ultimate challenge for meteorologists and climate scientists is the modeling of clouds in a warming world. Clouds both warm and cool the planet, and small changes in their type, height, and coverage could either dramatically accelerate warming or help slow it down. We need better models to understand how a warmer atmosphere will change the ratio of low cooling clouds versus high warming clouds. The fate of the future forecast may hang on the delicate, beautiful, and utterly complex physics of the cloud. And so our deep dive into the colossal engine of Earth's weather draws to a close. We've journeyed from the distant, unfair fire of the sun down through the layers of the atmosphere, watched the colossal currents of the ocean turn straw into weapons, and seen the air itself turn into a spinning, life-giving battery of heat. You now know that the world above your head is not random chaos. It is a vast, interconnected, and beautiful machine, constantly striving for balance. As you settle in tonight, maybe you can imagine the quiet physics at work all around you, even in the stillness. Think of the air pressure settling down, slowly pressing out the wind. Think of the water vapor in your very room, waiting patiently to condense onto a cool window pane as dew. Imagine the mighty jet stream, miles above you, flowing like a silent, fast-moving river, guiding the clouds that will bring tomorrow's forecast. This entire global engine, for all its power, has a deep underlying rhythm. The rotation of the earth, the rising and falling of the tides, the slow, steady flow of the Gulf Stream. These are the forces of nature that run on a geologic clock. They are the calm constants beneath the daily surface storms. Even the most violent storms are part of a cycle of renewal. The heavy rain cleans the air of those tiny dust specks, leaving the air fresh. The thunder, for all its booming sound, is merely the shockwave of cooling, a sign that the atmosphere is rapidly finding equilibrium. Now, let the thought of this massive, intricate, and ultimately predictable system bring you comfort. Allow your mind to release the stress of the day and begin to drift on the slow, steady currents of the atmosphere. There is nothing you need to control. The powerful engine of the planet is running perfectly, even when we are resting. The clouds are in their place. The winds are doing their work. The heat is being transferred. The science is settled. The physics is perfect. And the sky is keeping its ancient, quiet vigil. Let the knowledge that you are part of this enormous, magnificent system be a gentle weight that helps you sink deeper into your pillow. Let your thoughts be as soft and slow as snow falling outside, or the sound of the ocean currents far below the waves. The atmosphere is a place of profound science, but it is also a place of peace. It is the great, soft breath of the planet, circling endlessly, carrying the calm of tomorrow's dawn. Thank you for joining me on this deep, quiet exploration. If you've enjoyed this gentle journey into the facts about weather, and if these calm, scientific explanations helped your mind slow down and settle, I invite you to subscribe and return again. There are many more nights of sleepy science and story waiting for you here. But for now, let the winds settle, let the thoughts fade, and let the quiet knowledge that the world is spinning perfectly guide you into deep rest. I'll see you next time here on Sleepy Zone. Good night.